Okay, now we want to use the dot product to look at another application and describe planes in Rn, right? We started with lines. Whoops, that's not the eraser. We started with lines in Rn, which were one-dimensional subspaces. And I should say linear, right? Because nonlinear curves are also one-dimensional subspaces. And now, like I was saying in a previous video, you always start with, in math, you always work your way up. You start with something simple that you do know, and you ask, how can I use that to understand something I don't know, right? And so the simplest subspace you could look at is a one-dimensional line in Rn, and the next step would be to look at planes in Rn, because these are linear in a sense, right? There's no curvature to a plane. And so now we're going to look at planes in Rn, which are linear 2D subspaces, right? And let's kind of reinvent the wheel here. I could just tell you, here's the equation for a plane in Rn, and you could use it to find an equation for a plane, or to find the shortest distance between a point and a plane. But let's kind of reinvent the wheel here and understand why these equations are what they are, if you will. So let's start with a plane. So this is a plane living inside of Rn, right? I don't know why I wrote R2. So we have this plane in Rn, and we want to ask ourselves, what is an equation for this plane? And let's see if we can construct an equation on our own without being told what it is. So what do we need? Well, to understand an equation for a plane, we need a setting or a base point, right? So let's say we know some point P. And let's say P is a fixed point on the plane, right? And so here we'll give P the values P1, P2, up through Pn in coordinates. And let's pick another point Q on this plane, but we're going to let Q vary. And I'm going to say that by saying Q is arbitrary. So let me say arbitrary and not fixed point on the plane. And since this is arbitrary and not fixed, that means it can vary. And so let's give Q in coordinates, let's give it variables, say x1 through xn, right? And now for any point on the plane, Q and P, we know the vector PQ also lives on the plane. In fact, you get a family of vectors. As Q varies for every point on the plane, what you get is this family of vectors, right? And so what we could try to do is try to describe this plane based on that family of vectors, right? And so here's kind of a conjecture. Or maybe not a conjecture, since I'm stating it as a question. But here's a conjecture. We can describe the plane I want to say in terms of, or let's say using the family of vectors PQ, right? That's kind of our conjecture, is that, okay, well, as Q varies for every point on the plane and P stays fixed, well, then this family of vectors should map out that entire two-dimensional subspace, right? And so this family of vectors should be synonymous with this plane here. And now you may ask, right, the next thing is, okay, how would we go about proving this conjecture, right? Or verifying that our conjecture is true, right? We don't know if it's true at this point. That's why it's a conjecture. If this were to be true, then we would need a way to explicitly describe this family of vectors, right? I mean, we can, in a sense, we can say what these vectors are, right? Well, if P is the point P1 through Pn and Q is the point X1 through Xn, well, then we can write that PQ is the vector X1 minus P1, X2 minus P2, et cetera, Xn minus Pn. And if you let P1 through Pn be fixed numbers, and then let X1 through Xn vary, right? So X1 through Xn, these are points on our plane here. I would hate to call the plane P because we're using the point P here. Let's call the plane smiley face. So this denotes the plane. Okay, so then X1 through Xn are elements of smiley face because they belong to this plane. And so if we let these vary, this is our family of vectors, right? But how can we don't want Q, right? How do we guarantee that these points Q are necessarily on the plane, right? Because, you know, beforehand or a priori, the point Q could be whatever, right? Q could just be an element of Rn, and it could be way off, you know, somewhere else. We want these points Q to be on the plane, but how do we guarantee that, right? Because if you were to not try and guarantee that and you would get some equation, well, then you would have no restriction, right? You could find points not on the plane that would satisfy your equation, which means, well, then your equation wasn't actually representing a plane. And so so here's a question. In trying to solve our conjecture, right? We've come across a little bit of a roadblock here. So here's a question. How do we guarantee? I can't spell the word guarantee right now. My English teacher father would be pretty happy with me. How do we make sure that the points X1 through Xn are indeed in smiley face? And moreover, we don't even need, like, it's not enough to just guarantee that those points lie in the plane. We also need to guarantee that once we have an equation, it only works for points on the plane, right? Because we only want that equation to be expressing points on the plane. So I won't write all that down because answering this question will take care of itself. So how do we do this? Well, let's step back from this kind of algebra and element-wise understanding of our plane. Let's look at the geometry of this again. Right? The points Q are restricted to this plane. And so how could we describe that restriction, right? Well, a plane is flat. That's not very mathematically rigorous, but a plane is flat. It has no curvature to it, right? Which means you can construct a vector that is perpendicular to your plane at every point. And we call this a normal vector. So let's let N denote a normal vector. And this means that it's perpendicular to the plane, which we're calling smiley face, right? And so our normal vector right? It's true. If it's true that this vector is perpendicular to the plane at every point, well, then it's certainly perpendicular to the plane at point P. Now, using this notion, and let's give this normal vector a description and coordinates. Let's call this A1 through AN, right? I'm not going to use N, so I don't have like NN, right? I don't want to confuse the lower case N for a vector and subscript. So here, the components of this normal vector are going to be A1 through AN. Now, can we use this to realize this restriction on Q, that these points need to be in the plane? Well, what we know is that for every vector PQ on the plane, on smiley face, we necessarily have that N, so I'll introduce some notation here. N is perpendicular to PQ. And this is true for every vector on the plane, right? This upside down T here means perpendicular. We have a way of understanding perpendicular in like two perpendicular vectors in terms of the dot product. So what our restriction is really saying, remember that two vectors are perpendicular if and only if their dot product is 0. And so we can explicitly describe the restriction of these vectors PQ. They must be vectors PQ such that the dot product of your normal vector with PQ is 0, right? If these are truly perpendicular, then it's forced to have a dot product of 0 with the normal vector. And this uniquely determines a plane. And this is called the vector equation of the plane. So sorry here. So this is the vector equation of the plane containing point P with normal vector N. Okay, and this is the vector equation. And so if you know a point on the plane and a normal vector, then you can describe the equation for this plane. And so this is the vector form. We're more used to seeing, so like in R3, for example, we were used to seeing planes be able to form like AX plus BY plus CZ equals D, right? This is your general formula for a plane. Our vector equation, sure, it describes this plane, but not so explicitly, right? Or we understand that the plane must satisfy this, but it doesn't give us a good understanding or intuition of what's going on here. And to get that, or to get an explicit equality here, let's expand the left-hand side of this equation. Or not expand, but let's be more precise about what we mean, right? So the normal vector, we're calling A1 through AN. And remember, we're calling PQ X1 minus P1, X2, et cetera, et cetera. So to say that N dot PQ equals 0, well, that's equivalent to just being more explicit here. Not even equivalent, it's just rewriting, right? This is A1 through AN, and we're taking the dot product of this with, and then PQ here was this X1 minus P1 through Xn minus Pn, and we necessarily have that this is 0, right? Well, let's take the dot product. We know how to take a dot product. This means that A1 times X1 minus P1 plus, and I'll write one extra term here just for clarity, X2 minus P2 plus, et cetera, plus AN Xn minus Pn, this equals 0. Sorry, that's a 0. Okay, this is a good description. we'll put it in, just doing some algebra here, just convention to put it in what we call the scalar equation for a plane. So if we distribute at each term, we have a1x1 minus a1p1 plus a2x2 minus a2p2 plus blah, 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 plus an xn minus an pn equals 0. Then if we keep all of the terms with a variable on the left and move everything that's a constant to the right, then we'll have our scalar equation for a plane. So we would have a1x1 plus a2x2 plus blah, 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 plus an xn. And this is equal to, so let's just be kind of more compact here, and let's just say b, right? We can combine all of the constant terms here. So what would the constant terms be, right? a1 p1, a2 p2, an pn, right? You add all of these over, and so this is where b equals the sum, I goes from 1 to n of ai pi here. So you're just taking the sum of all of these here, right? And so this is called the scalar equation for, blah, 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 like for the plane containing point P with normal vector n. And I really want to point out that the coefficients to every variable is precisely the normal vector, right? The normal vector n was a1 through an. And so if you have an equation for a plane, like let's come back up to R3 here, like this example. This plane necessarily has a normal vector given by ABC, right? And so we have this duality where we can kind of obtain information about the normal vector from the scalar equation, or from the normal vector, we can obtain information about the scalar equation. Cool. Let's do a quick example here. Right? Because, all of this is in general, it's for an arbitrary dimension n. Sometimes it's nice to kind of do an example where we can picture or understand what's going on. So let's look in R3. What we want to do is we want to find the scalar equation of the plane containing point P, which we'll call, or the point 3, -2, 5, which we'll call P, and orthogonal, this means normal, to the following vector. We have n is given by -2, 4, 1. Okay. So let's find the scalar equation by way of finding the vector equation, right? And so what do we need? We need a point Q, X, Y, Z, such that PQ dot n equals 0. I just realized I flipped the order here, but that doesn't matter because the dot product is commutative, right? And so what is PQ? PQ is going to be the vector x minus 3, y plus 2, z minus 5. And then the dot product with -2, 4, 1 should be 0. So what do we get? Let's go to the next page here. This means the scalar equation for the plane is -2 times x minus 3 plus 4 times y plus 2, and then 1 times z minus 5. And this is necessarily equal to 0. And now we can put it in this kind of by convention, we just put it in this standard form here. So then we would have negative 2x plus 6 plus 4y plus 8 plus z minus 5 equals 0, which means we get negative 2x plus 4y plus z equals, looks like we're going to have negative 9 because we have 14 minus 5 on the left-hand side, which would be 9. You subtract it, you get negative 9. So here's the equation for the plane, right? And remember, what was our normal vector? Our normal vector was negative 2, 4, 1. So that checks out. Okay. There is one more thing we can understand via the dot product with planes, and it also ties in the projection vector that we were examining earlier. So let's look at finding the shortest distance from a point to a plane. Okay, so what do we have, right? We have a point. Let's call this point R. And then we have a plane here. Okay, and you want the shortest distance, right? There are many different trajectories to this plane, right? And we want the shortest. In other words, what we want is the minimum of the distance function, right? We have a distance formula for a formula between 2 points. Well, if you let one of those points vary, then it becomes a function, and you would want to, using multivariable calculus and partial derivatives, you would want to find the minimum of the distance function. But we can do this using the dot product to avoid such gross Calc 3 computation. Okay, so let's say we have this point R, and then we have the plane here with points P and Q. Okay. If P is a point such that RP, the vector RP dot PQ is 0, then RP is perpendicular to the plane, right? This is just based on our dot product principle here, right? We have a vector RP, we have a vector, or maybe we could say QP. It doesn't really matter, right? Because it would just be the negative. And so the question is then, to find the shortest distance from a point to a plane is going to be the trajectory such that your trajectory is perpendicular to the plane, right? That would be shorter than having some angle that's not pi over 2, right? And so basically what we need, the shortest distance here, is going to be equal to the magnitude of RP, right? If we can find the magnitude of this vector, well, then that would be the shortest distance. How do we do that, though? How we can do that is we don't know what P is, right? We just said there's some point down there on the plane such that RP is a normal vector. Let's say we know one point on the plane, Q. How could we get the vector RP? Well, we want the projection. So here, RP is going to be the projection of the vector RQ onto some normal vector, right? Because this is a specified distance. There exist many normal vectors, let's say N here. And we need, right, there are many normal vectors here, and we need the projection of this RQ onto the normal vector. This would give us RP here. Or if, yeah, so projection onto the normal vector here, right? And so what would this be explicitly? This would be RQ dot N over magnitude of N squared N, right? And so we have this formula here. And let's understand what the magnitude of RP would be, right? Well, this is going to be, well, let's not go into that. You would want to calculate the vector first, right? You would want to calculate this projection vector first. You'll get some vector that's a scalar multiple of your normal vector. And then that result, you take the magnitude, that's the shortest distance. So this video is getting a little lengthy. I've put a lot of information on today. So I think I'll stop here. And after the lab on Thursday, we'll then start to talk about the cross product. But I think this is all I've wanted to talk about for the dot product and its applications.